Now this is separation of variables for engineering diffusion type problems. Now the separation of variables is one of the oldest techniques for solving initial boundary value problems, and applies to problems where 1, the PD is linear and homogeneous, and 2, the boundary conditions are of the form given here, where alpha, beta, gamma, then delta are constants. Now the boundary conditions in this form are called linear homogeneous boundary conditions. Now here, let's apply it to a specific problem. Our PDE is u of t alpha squared u xx, where don't forget that these are partial derivatives with respect to these. Now x is contained within 1 and 0, and t is contained within infinity and 0. So our boundary conditions are 0, and initial conditions are phi of x, where x is contained within 1 and 0. Now we draw the rod example here, where u of x naught equals phi of x, and this is the initial temperature at steady state equals 0, where u equals 0 is the heat sink. Now above is a finite rod with temperature at both ends set to 0. Now our goal is to find temperature of u of x of t at later points in time. Now overview. A separation of variables looks for simple solutions to the PDE of the form u of x of t equals x of x t of t, where x of x is some function of x and t of t is some function of t. Now solutions are simple because only temperature of u of x of t of the form will retain its basic shape for different values of t. Here I've drawn a little graph just to represent different values which we're plugging into. The general idea is that it is possible to find an infinite number of solutions to the partial differential equation, which of this same time satisfy the boundary conditions. These simple functions, u of n x of t equals x of n of x t of n t of n of t, are called the fundamental solutions and are the building blocks of our problem. And the solutions u of x of t we are looking for is found by adding the simple fundamental solution here in such a way that we have the resulting sum here, which satisfies the initial conditions, in as much as this sum still satisfies the PD and boundary conditions. We now have a solution to our problem. Our separation of variables. We wish to find a function u of x of t that satisfies the following 4 conditions here. To begin with, we look for solutions of the form u of x of t, and x of x t of t, by substituting this into our PDE and solving for this by the usual process of separation of variables, and making the substitution, it gives this equation. Now we're dividing both sides by alpha squared x of x t of t. We get this here, which you should probably all be familiar with by now. And now each side must be equal to a constant. So we get t prime equals minus k alpha squared t equals 0, x double prime minus k of x equals 0. So now we can solve each of these two ODEs, multiply them together to get a solution to our PDE. Now note that we have essentially changed the second order PDE to an ODE. However, we now make an important observation, namely that we want the separation constant k to be negative, or else our t doesn't go to 0 as t goes to infinity. So we'll choose minus lambda squared as it's guaranteed to be negative. Now we now write t prime plus lambda squared alpha squared t equals 0, and likewise for our x double prime. Then both are standard ODEs and have solutions of this form here, where A is an arbitrary constant, which leads us to these equations here. So, and all our functions are the form where A, B, and lambda are arbitrary, and these will satisfy our PDE that was already given here. But this has infinite solutions. We need solutions that satisfy the boundary conditions and initial conditions. So we choose a certain subset of our current crop of solutions, namely this, that satisfy our boundary conditions u of 0 of t and u1 of t equals 0. To do this, we substitute our solutions into the boundary conditions and we get this form. Now, this last boundary condition restricts the separation constant lambda from being non-zero number. It must be a root of the equation sine theta equals 0. In other words, in order that u of 1 of t equals 0, we get these values for lambda. And note that the boundary condition could also apply if a equals 0, but that's trivial, so we're disregarding that. We now have finished the second step. We have now found an infinite number of functions, namely this. Now, finding solutions to the PDs and boundary conditions and initial conditions, we need to add fundamental solutions in a way that picks coefficients of A, that the initial conditions are satisfied, which leads to an interesting question posed by Fourier. Is it possible to expand the initial temperature of phi of x as the sum of elementary functions, given here? Which is yes, provided that phi of x is a reasonably well-behaved function, is continuous. Hence the question now becomes how to find the coefficients a of n from these equations, and we'll keep going where they become more and more wavy as we keep adding more and more terms and so on. Now this is actually pretty easy and uses a property of the function sine of n of pi of x, where n equals 1, 2 and so on, known as orthogonality. Now these functions are orthogonal to each other in the sense that our integral of 0 to 1 of sine m pi x and sine n pi x of dx equals 0 if m does not equals n, and 1/2 if m equals n. So we now solve for the coefficients of this. We multiply each side of this equation by sine m pi x, where m is an arbitrary integer, and integrate from 0 to 1. Doing this, we get this here. And all of these terms drop out due to orthogonality. So solving for a and m gives this. And this is our coefficient for a and m. Now, so the solution is given here. U of x of t equals the sum n equals 1 to infinity a of n e to the n pi alpha squared t and sine n pi x, where the coefficient a n is given here. Now note, observe that the ordinary difference between Fourier sine expansion of phi of x and the solution to the insertion of time here in each term. If our initial conditions were a very simple expression like this, then our solution would simply be this here, which in this case is obvious that if we expand phi of x as a Fourier sine series, we get a equals 1, a2 equals 0, a3 equals 1/2 and so on, a4, a5 equals 0. The terms in the solution, u of xt equals a1 e to the minus pi alpha squared t sine pi x plus a2 e to the minus 2 pi alpha squared t sine and so on are functions of x and t. We note that the terms are further out in the series get very small. First, due to our negative exponential. Hence, for long periods of time, the solution is approximately equal to the first term here. Now, which is the shape of the damped sine curve, where phi of x is the initial temperature. So, when graphed here, t equals 0, t equals 1, t equals 2, 3, and so on. higher order terms damper faster in diffusion problems. Now that's the our third lecture, I think, on this engineering mathematics. So please do like and subscribe.